finish up chapter 9 here, we're going to take a look at what's called plane curves and parametric equations. So here's the standard math definition that you'll see. Certainly don't want you to write it down, just kind of understand what's going on, then we'll take a more straightforward approach to it. So you let f be a function f, you let y be some function g, so they share some common domain. If you collect all the points for x and y, you basically get two functions together here. Now, functions we know pass the vertical line test, so each f and g are functions, so you can put a straight line through them and it only hits once. But when you put these parametric things together, they won't be. So it's a neat little way we can get around the definition of functions. So when you do this, you create what's called a plane curve. X is function f, y is function g, and you're taking x comma y's and you're graphing them. So these are what's called parametric equations, and t is your parameter. Blah, 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 blah. Here's what it really means. Parametric equations describe movement along a curve, so it lets us look at some things like this. So this picture here, clearly not a function, but it's two separate parametric equations, one for x, one for y, are functions. So as this guy moves along a curve, you can see these directional arrows. It creates this pattern. Okay, and we do that with two separate functions that we graph together. This guy here called the torus or donut. If you graph these three parametric equations, so it's got to be three dimensions, things you guys have seen before in here, sines, cosines, maybe not the big R or whatnot. But if you take these three things and you graph from 0 to 2 pi, you will get this shape. So then you can do all kinds of interesting things like, well, what if you are on this plane? What does it look like to you? What does it feel like? Different stuff like that. What if you want to do geometry on this surface? Here's two more. This is the butterfly curve. It's mapped with these two parametric equations. So a sine of t, you've seen e's raised to powers, all kinds of stuff. You've graphed 2 cosine of 4t before, a sine to the 5th. So it's a butterfly curve. It's in 2 dimensions, so we only have 2 equations. These two things written in polar form is this. You've seen r's, sines and cosines together tell us how we represent these in polars. This guy here, the parametric helix, is represented by these three. So z is b times t. I'm assuming b is just another little variable. And this guy will just keep spiraling up like that. So there's some little applications of what we can use parametric equations for. What we're going to do with them is basically this. It's going to show the x position at a certain time. It's going to show the y position at a certain time. And that's going to map out our curve for us. Okay? Like I said, we use it with conics because by definition, everything we've graphed so far this chapter are not functions based off the vertical line test. But if we do them parametrically, each of the individual things will be a function. And then you can put them together and you can kind of get around that definition there. So we're also going to use them with velocity stuff, which should look very similar to you guys who've had physics recently. Okay, first thing we're going to look at is how we actually graph these things. So discuss the curve given by parametric equations. What you're going to see, they're going to give you an x for one parametric equation. They're going to give you a y for a second one, so we know it's 2D. We're not going to be graphing goofy things. And this guy here will give you your domain. So we're looking at t's from -2 to 2. So here's how we kind of do this. See what happens at the endpoint, and then you try and figure out how you connect the endpoint, and then you fill in everything in the middle. So kind of a few little notes over here if you want to pause it and read through those. This is what we're going to do. So we're going to take some times, some x's, and some y's and figure out all the points. My domain says I start at -2 and I end at 2. So those are the values that I'm going to look at first. So you literally just have to go here. Okay, if t's in -2 and you plug that in, no matter what your calculator tells you, you're going to get a 4. Okay, if t's in -2 and you plug it in there, you're going to get a 0. Now do the other endpoint. So if t is a positive 2 and you throw that in there, you're still getting a 4. If t is a positive 2 and you plug that in there, you're getting a 4 as well. So that's 2 points. Okay, it doesn't tell us what happens in between, which direction the arrow goes. So we need some more things. So simply just pick some more points. Okay. Once you do that, you guys can easily plug these in. I'll just do one here real quick. So let's say you plug in a -1. -1 squared is 1. -1 plus 2 is 1 as well. You fill in the rest of this table, and you'll get something like this. This table here just grouped them together. We would just take these 2 points here and say 4, 0. So if you graph them in this order and you connect them with the arrows, there's your curve. Each of these guys was a function. T squared is a parabola, t plus 2 is a line. They pass the vertical line test. You put them together, you get this curve right here. Not a function, but each of them individually were. There's your curve, and you can see the arrows heading up in that direction there. Okay, so there's one thing. Next topic, how do we convert to rectangular coordinates? Okay, so it's asking us, here's the same parametric equations, but how are we going to get that parabola there in rectangular? So we're basically graphing rectangular things in rectangular, polar, and parametric. If you can solve for t, you can substitute to get rid of it. So what you need to do is just consider this as x equals t squared and y equals a t plus 2. This guy is definitely easier to solve for t, and all t is a y minus 2. This guy you would have to square root, and you don't want to worry about that because you end up with positives and negatives. Do a substitution here. No need to double distribute because that matches up perfectly with a parabola. I guess that's not squared. And this should have an x minus h quantity square. Sorry. This is the one that's squared, and there's your x minus h. So we would know our center or our vertex is at h comma k. It's a y squared, so it's opening to the left or it's opening to the right. In this case, with what we have, our center or our vertex is at 0, positive 2. And you could find the a if you wanted. It would have to be 1/4 here. Okay, that would help us find our lattice line and everything, because we know that that has to equal a 1. Like we said, it's a y squared, and it would come out to a parabola with a vertex at 0, 2, and it opens to the right. You can do these guys in your calculator if you want to try and put it into parametric mode, like when we did polar graphing stuff. You can try that, but we'll take some time in class to look at that as well. Okay, what if I gave you this? So convert this parametric equation into rectangular. Now there's going to be 2 ways to do it. First thing you notice is, here's your x, and notice they didn't put the of t, but I guess it really doesn't matter because we just ignored it last time. And they also didn't give us anything for the domain. So domain's really anything you want to be here. First way is just like we did last time, is a table. You got x equals a cosine t and y equals a sine t. So basically you're trying to plug in values of t. If you're doing sine and cosine, pick those values that we've been using all year. Okay? See if you guys can fill in your table, and we'll pick it right up in part 2.